Hello YouTube, and welcome back to another video. In the last video, we talked about references, and references are another important part of Motion Canvas. You've used them before, or we've at least talked about them before, where if we wanted to manipulate or modify anything for animation purposes in Motion Canvas, you need a reference to your object in order so that you can manipulate it or do whatever you need to do. So if you wanted to scale, you needed reference to your circle. And so we talked about how to create a ref, make a ref. You can have an item and dynamically create an array of references, or dynamically create your reference. Even use custom functions and create references to your custom functions in make refs in many different ways. So if you haven't seen that video, please go watch it and then come back to this one. This video is about tweening. We're finally talking about tweening. Tweening is another important aspect of Motion Canvas that we have already went over, but we haven't actually talked about tweening or what it really is. For example, this radius example, or this default 2 example, I said this does the animation in 2 seconds, does the animation in 2 seconds. What is that whole concept? It's called a tween. Tweens are one of the fundamental building blocks of animation, as I said. They are a special type of generator that animates between two values over a given time. So tweening comes from between, from point A to point 2 or to scene 2, and how much time are you going to spend between those two states. The simplest way to create a tween is via the tween function. So this is the tween function. So in the example above, we animate X. So circle, here's our reference from last time. We have position X, and we're mapping the position of X to this. So we are animating the X coordinate of our circle from negative 300. We start from 300 to positive 300 over a span of 2 seconds. 2 coming from here. Okay, so we have 2, and then our callback, which our callback just sends in this value. That's what it is. The first one specifies the tween duration in seconds. The second is the callback function that will be called each frame the tween takes place. The value parameter it receives, so I guess this value parameter it receives is the number ranging from 0 to 1, informing us about the progress of the tween. So I was a little wrong. This value isn't 2, it's 0 to 1. So it could be 0.0001, 0.0002, all the way to 0.7, 0.8, 0.9, all the way to 1. It's like a progress bar. Informing us about the progress of the tween. We use it to calculate the values that our tween animates. In the case of our circle, we use the function map to map the value ranging from 0 to 1 to negative 300 to positive 300. So you can see that it takes 2 seconds at each frame, either 30 frames a second, 60 frames a second, whatever. It needs to calculate how far is it from our beginning to our end. Think of it as a progress bar. Timing functions. At the moment, our animation feels a bit unnatural. The speed at which the value parameter changes is constant, which in turn makes the circle move in a constant speed. In real life, however, objects have inertia. They take time to speed up and slow down, and we can simulate this behavior with timing functions. A timing function takes the number in range of 0 to 1 and returns another number in the same range but with a modified rate of change. Motion Canvas provides all of the most popular timing functions, sometimes called easing functions, but since it's normal JavaScript functions, you can just create your own. So let's use the ease in and out cubic function to fix our animation. So you can see it speeds up and then it slows down real quick. Ease in out means that the object will speed up at the start, the in, and slow down at the end, out. Cubic denotes the mathematical function used. In this case, it's a cubic equation. Knowing that, a function called ease out quad would make a object start with full speed and then slow down at the end using a quadratic equation. The effect of a particular easing function can be visualized by animating the y-coordinate of an object as the time changes with a constant rate, such as bouncing in and out. So here we can see as time goes at a constant rate, the value will change from 0 to 1. Nice. Because using timing functions to map a range of values is a really common practice or pattern, it's possible to skip map entirely and pass the range to the timing function itself. So this can be modified to be just this. Interpolation functions. That's a big word. So far, we've only animated a single numeric value. The map function can be used to interpolate between two numbers, but to animate more complex types, we need to use interpolation functions. Consider the following example. Before I get to that, I do want to point out that what this was saying is we could theoretically create our own function here as long as it returned a number between 0 and 1, and we could have it gradually increase according to whatever parameters we pass in. So we can create our own timing functions. Sorry. Back to interpolation functions. So we consider the following example. So far we've used a single animation, single numeric value. We'll need to use interpolation functions to consider the following examples. So we import color. You tween, so for 2 seconds. Color fill, color, whatever that is. New color, ease out cubic. Lerp is a static function that interpolates between two colors. Mind reader. So in this example, we are changing between the two different colors. That's pretty cool. You could also do a color dot fill, I think, from one color to another, but this is another way of doing it. I'm hoping that we talk about the other ways of tweening that are built into the different classes. All complex types in Motion Canvas provides a static method called lerp that interpolates between two instances of said type. Aside from the default linear interpolation, some types offer more advanced functions, such as vector to arc lerp. It makes the object follow a curved path from point A to B. That's cool. So we're going from this path to this, and so with normal tweening that you would use to change from one location to the other, it would just start here and go over here within a straight line. If you want it to be more of an arc, you could do this kind of tweening function or notation to get it to be more in an arc. The degree of the arc, I don't know. I'm sure that you could modify this some more. And actually, we can click here and see, do we actually get the... No, we do not. We do not get a the degree of... Actually, maybe 0. Maybe you can set the radius. Tweening properties. The tween function is useful when we need to orchestrate complex animations. However, there is a better way of tweening individual properties. You may recall from the quick start section that the following tweens can be written as this. This is what I was talking about earlier. This is a better way of doing it and easier than doing this. Here we use a signal tween. Oh my gosh. They have combined signal with tweens, which looks similar to a setter, except it accepts a translation duration as its second argument. Again, what I talked about in a previous video of how things just come together perfectly as a prediction. I said it was a signal. That's also used as a tween. It's called a signal tween. Mind blown. Under the hood, this will also create a tween, one that starts with the current value and ends with the newly provided one. We can chain multiple tweens together by calling the to method on returned objects. Again, we've used to already. We know this. We can add more to functions as more of the chain to modify the initial radius or to modify an initial value. Under the hood, this will create a tween. Yes, we've went over that. By default, property tweens, which is what this was, use in and out cubic as the timing function. This can be overwritten by providing a third argument. I did not know that. That is interesting. Similarly, you can pass in a custom interpolation function as a fourth argument. So you can do vector to arc lerp. That's nice. Spring functions. Oh my. A spring function allows us to interpolate between two values using Hooke's law. We need to provide it with the description of our spring and the from and to values. You can think of it as having a spring in the resting position, the to value, stretching it all the way to the starting position, the from value, and letting go. The movement of the spring as it tries to reach the equilibrium is what we can use to drive our animation. In the example below, we use springs to animate the position of a circle, but this method can be used for more things than just position. So we have our reference to the circle, which is right here. We have a spring, plop spring. Plop spring is right here. So that's the type of spring we want. We have from negative 400 to positive 400. We want to do it in 1 second. And we want to change the value of the X position. And then we want to do it again in reverse using this smooth string. So let's take a look at the animation. Cool. So plop string, you can see how it goes back and forth. And we pull it back with smooth spring and we let it go. You really get this springy vibe. You could probably use this as text if you wanted to give some imagery if you wanted to be a little fancy. Spring description. The first argument of the spring function expresses an object that describes the physical properties of our spring. So plop string and smooth spring is our description. Motion Canvas ships with a few useful presets that you can use, such as plop string, smooth spring, but it's possible to define our very own spring. So we have our mass, our stiffness, dampening, initial velocity. Our mass describes the inertia of the spring, how much force is required to accelerate and decelerate it. The stiffness, the coefficient of the spring, usually represented by K in Hooke's equation. It describes how stiff the spring is. Dampening. Over time, dampening causes the spring to lose energy and eventually settle in equilibrium. You can set it to 0 to create a spring that oscillates indefinitely. So this would be really cool, where if I, let's say, wanted to do an animation where I just had a little ball that bounced back and forth between 2 points. Let's say it was a packet of information. I could use a spring in that example and just have it go back and forth indefinitely. Or I could just have that circle as part of a yield and just have a bunch of yield statements, or a yield in a for loop. This just gives us more options. And initial velocity. Initial velocity of a spring, you can set the from and to positions to the same value and give the spring some initial velocity to make it accelerate in place. Settle tolerance. Notice how in our spring example, we provide the first spring with an additional value right here. I said it was the time. Maybe it wasn't the time. I thought it was. Apparently it's not. It's settle tolerance. This optional argument called settle tolerance is used to define the minimal distance from the to value to the spring should reach to be considered settled. The generator created by the spring function finishes only when the spring settles. By adjusting the tolerance, we can make the animation finish faster, depending on our needs. In our example, we animate the position to a tolerance of 1, means the spring needs to be at most 1 pixel away from the to value to finish the animation. So if we watch this again, so it will go back and forth forever until it meets this tolerance variable. So once it's 1 pixel away, it will say, hey, we're done. We're going to stop going back and forth. Otherwise, you could potentially have it go forever. Sorry. I don't know why Google just talked behind me. Saving and restoring state. All nodes provided a save method, which allows us to save a snapshot of the node's current state. We can then use the restore method at a later point in our animation to restore the node to the previous state. So we can do circle save, change the position, and then hit restore. It's also possible to provide a custom timing function to the restore method. Node states get stored on a stack, which makes it possible to save more than one state by invoking the save method multiple times. When calling restore, the node will be restored to the most recently saved state by plopping the top entry in the state off the stack. If there's no save state, the method does nothing. The example shows a more complicated example of how we can store and restore multiple states across the animation. So we have our circle, we save the state, we change the position, we change the scale, we save the state again, we change the position, We change the scale. We save it. We do it again. Now we restore. We take, what was it? 1 second, I believe. Let's see. Remove, save, down, over, and then we do things in reverse. 1, 2, 3, 4, 5, 6. So I think that is 1 second. In any case, we're done with tweening. You should now be an expert on tweening. We're going to continue timing and using time in our animations in the next video, time events. If you have any questions about tweening, leave a comment down below. If you like this comment and you like how things are going, hit the like, hit the subscribe, continue watching more videos. It really helps out the channel. Until next time, have a great day, and I will see you later.